Hello there. I hope you are having great times. And today's Friday, so let's start with our lab. So let's go to the syllabus and let's see where we are now. We're at lecture 4, which is open circuit test. We have covered module 1, lecture 1 and 2. We're done, and in module 2 we have done experiment 1. Now, today we're going to do experiment number 2, which is open circuit test. Let's open experiment number 2. So, although it is 2, but it says 3, it's a mistake. So, you can ignore that one. So, this is experiment number 2. So, this is an open circuit test of a single phase transformer. So, uh, the purpose of this experiment is to actually measure core losses in a transformer, especially single phase transformer. We can do this for three phase transformer as well. So the procedure will be the same. So if you know about this one, like single phase one, we can easily do it for the three phase. So in industrial level, they do it for single phase or three phase, you name it. So it's better to start testing it. So there are two types of losses in a transformer. One is there are many losses, by the way. So the major losses are core losses and copper losses. So we are gonna learn how to measure core losses. So to do that, let me open another one. Um, so I have another slide prepared for you guys, which is this one. Let me open it full screen. Okay, this, although I'm not supposed to cover the theoretical part that much, but I'm gonna do eventually. So for this experiment, we need to actually review some of the power equations. So this is true power, this is reactive power, so it is Q, and this is apparent power. So these are the formula. We all know these, so these formulas can be used in different ways. So we'll be needing them, and also we need to know about this power triangle and this equation, especially. So power factor, that is also important for this experiment. So I hope we all know this. So energy losses. So we are going to talk about practical transformer in this case. So there will be losses in practical scenario, right? So I told you there are two major losses. One is called core loss, another one is called copper loss. So in this experiment, we're going to learn how to actually calculate the core losses in a transformer. So core loss can be also denoted as iron losses. So while designing a transformer, you can actually reduce the amount of core losses by selecting very good iron material. So, and also if you if you look at a transformer's figure, then we can see that the winding is wrapped around core material. So this could be a block of iron, but in reality, uh, what engineers do is they slit the whole thing into smaller pieces, tin sheets. So they stack one on top of each other. So they make a block out of it. So they don't actually use solid iron core. So they actually use laminated slates like this so that they can actually reduce the amount of eddy current losses. So you can you need to do this beforehand while designing the transformer, and while manufacturing it you need to follow this, otherwise the eddy current loss will be huge. Same goes for hysteresis loss. So that is called eddy current loss. So if you don't do it properly, so the eddy current loss will be very high. And hysteresis is also a phenomenon, you can say, that any ferromagnetic material has. So it tends to actually retain some degree of magnetization after exposure to an external magnetic field. So um, it's just like when you actually fry an egg on a pan. After the frying is done, still there will be some residual heat left, right? So that is kind of a same thing what we are trying to say. So um, so this residual magnetism that is left behind create some problems. Like for instance, in AC cycle, like for instance, this is AC, this is an AC signal. So in positive, when it is in the positive side, so it gets magnetized. A magnet gets sorry, not magnet, like iron material gets magnetized. But after some time, when it reaches zero, it's supposed to be also demagnetized. Like it's supposed to act like an iron, not magnet, but it doesn't. So that is the problem. If the magnetization, uh, the residual magnetism is too much for that type of material, then it's not good for transformers. So we need to actually select material that has a very lean sorts of this pH curve. So it goes, and when it comes back, it doesn't come back to B0. It comes back to this point. I know you all know this pH curve, so I don't need to repeat it, but it's better to choose a very good material for transformer. Otherwise, this residual magnetism, because of this, um, there will be huge losses. Anyway, so these are the losses on the core. So there are some other losses, like for instance, the losses in the windings. So since this is an winding, so we can say that it will have inductances, and since these are made of copper, so there will be resistive losses, which is denoted as like in the combined effect of this resistance and reactive components will have copper losses. So for this experiment, we are not going to talk about that much about like copper losses. We'll talk about core losses. So in order to do so, we will do, let's say, this open circuit test. So before going to that section, I'd like you to actually see this figure. For an ideal transformer, when we learned about this, we saw only windings and that's it, right? But in this case, we'll see an exactly equivalent circuit of a actual transformer, single phase transformer. So this is the power supply, and this is the primary side. So you will have R1, that's the resistive component of the primary winding, and this is the X1, which is the reactive component. So uh, the combined effect of them will actually produce, will give us the value of impedance of the primary side. And this parallel branch represents the core. So the core will also have some resistive component and magnetizing component. That means inductance. Although uh, they are not solid, but they are a block of uh, iron, right? But that block also has some resistive component and inductive component, because uh, that block actually helps us to carry flux from one side to another. So we have that, and for the secondary side, we also have resistive component and inductive components. So this R1, R2, X1, X2, these are components of the copper and winding. So, and we have load here. So that's the equivalent circuit, and we can definitely simplify it. We can reduce this circuit to be very simplified so that we can actually calculate it, because if we have a core here, so there is no connection between E1 and E2 here, like, I mean, a physical connection. So there is no wire whatsoever. So we are actually using Faraday's law of electromagnetic induction. We are inducing EMF from primary side to the secondary side. So there is no physical connection. So that's if we want to calculate on the basis of this, it will be very complicated. There is another way, so we can look at this transformer in a different way. Like we can actually see every component, like for instance, R1, X1, R2, X2, with reference to the primary side. So we'll be trying to look from the primary side. So that can be done with the help of transformation ratio. In that case, the figure will look like this. So we can actually take the secondary side's resistance and reactance component and place it here. So every component like will be with referred to the primary in this case. And we can do the same for if we want to see everything from the secondary side, we can also do that. So in that case, that will be the equivalent circuit. This will be the equivalent circuit. And we can also uh, minimize the effect, simplify the equivalent circuit like this. It's not that important for this presentation and this experiment, but you need to know that there is a way to actually reduce it and simplify it further. Anyway, so let's talk about the open circuit test. So say for example, this is the transformer that we are gonna use. So if we choose to use the low voltage side as the primary, so we need to supply voltage to the low voltage side, and the high voltage side will be open. So we can, in our experiment, we are going to test both sides. We are going to supply to the low voltage side, and we are going to supply to the high voltage side, and the other side will be left open. And while doing that, we'll measure the input power, input voltage, and input current. So, and with the help of these sets of equation, we'll be calculating other um, component of this transformer. So it is to be mentioned that when we actually open this one, like the secondary side, it could be low voltage or a high voltage, it doesn't really matter. If we open this secondary side, there will not be any current. So I2 will be 0. In that case, this I2 prime will also be 0. So there will be no current circulating on the secondary side. In that way, I1 will be very low. So there will be current circulating here, but there won't be any current circulating on the secondary side. Why is that? Because there is no load. It's open, so there is no path for the current to go around. So this I1 will be very high, very low, and this one will go towards the, what is it called, core. And so it will, this no load current, I would say no load current or open circuit current, will go uh, to this path, and it will be splitted into two sections. One will be IC and another will be IM. And the amount of current is so small, it will not actually affect anything here. Most of the current will be gone here, and there won't be any voltage drop here at this point because the amount of current is very low. So we can actually, literally, we can actually replace this one with a short circuit. So we can ignore these component R1 and X1 because the amount of current is very low. So in that case, the circuit will look like this one. Okay, so there will be open circuit current going to these core elements. These are Fe and Xm. So, and we'll supply the voltage that we are going to supply will be also open circuit voltage, and the power that is generated here, it will be open circuit current. So I have a picture. Let's see. Where is that picture? I have already created that one. Just give me some moment. I have the video also that I'm gonna show you. Okay, so this is the picture that we're gonna talk about right now. So this is the figure I have talked about a few seconds ago. So we have open circuit voltage supplying to this core element, and this current is nothing but open circuit current, and this is the current flowing through this core resistance, and this current, which is I sub xm, is going through this magnetizing component or reactive component of the core. So there are two ways you can calculate uh, the values of this RC and XM. We need to actually calculate RC and XM, because if we can calculate these elements, we can actually get the exact amount of losses. So we can calculate, we can measure, we can calculate I square R loss and I square XM loss. So we can calculate everything here. Anyway, let's proceed. So the way one would be very straightforward. Um, while we are actually measuring, connecting everything. So in the video, I'll show you one demonstration. In that demonstration, you will see that there will be four components that we'll measure. One is VOC, IOC, and the cos theta and power, real power. So let me draw it somewhere. Let me see. How can I draw something? Okay, here we go. So VOC, IOC, and POC and cos theta. Let's say 0. Not 0. What should I write? Okay, some degree, some angle. Okay, so these are the four. Okay, why is it? Okay, it's visible, I think. So these are the four elements that we are gonna measure in our experiment that I will show. So we know all of this. So we know from this equation that RC equals VOC square over POC. So this is a very basic equation. So if we uh, uh, use VOC, the measured amount VOC, and POC, we can actually directly calculate RC. Same goes for here, but we don't know what QOC is. But we know this, right? So what we can do is we can calculate the apparent power from with this equation, and then after that, using this equation, we can calculate Q sub OC. So we can simply, using these uh, three formulas, we can actually calculate X sub M. There is another way which is also important. I want you to actually calculate using way one and way two. Way two is we can calculate cos theta, although we have measured cos theta, but we can also calculate it like so, POC sub SOC. SOC is nothing but the apparent power at open circuit test. So we can use these values to calculate cos theta. We can match it with the measured value. I'd like you to do them, like calculate them and match it with the measured value. Then from these, we can actually calculate, what is it called, sine theta. After that, since we know that these RC and XM are directly parallel with this power supply. So with this equation, we can measure the value of the current that is passing through this RC. So which will be I sub RC equals IOC times cos theta, and I sub XM will be IOC sin theta. And from with the use of Ohm's theory, Ohm's law, we can get RC and XM. So way 1 and way 2 will give us both RC and XM. So I want you to actually calculate all of these values using both the ways, so that we can have, let's see, you can create a table which will look like this one, where everything, so these red uh, values are measured values, and this is for the calculation part. So sin theta, QOC, IRC, IXM, and you need to calculate this using way 1, and this is way 2. So you need to calculate it for both the cases. And also there will be 2 more cases. In one case, I will be supplying to the primary side, and the secondary side will be open. And for the secondary side, if I supply to the secondary side, this will be the case 2. So the primary side will be open. So there will be 2 cases and 2 ways. So I'd like you to actually fill up everything, make a table which will have all of these values. So now let's go to this video where I actually recorded this earlier, where I conducted everything. Let's watch it. So this is the experimental setup of open circuit test. The theoretical background, I'll explain it in a different video. So we'll have to actually let's see if I can merge it, then it's okay, but otherwise, like, you'll have to actually put it side by side and actually compare the theoretical video and this experimental setup. Although I'm not gonna go into very much detail about the theory, but I'll cover the most of the part anyway. So we have power supply from here. We know that this is a power supply, and we're gonna use a single phase transformer. So we'll work on this side, and this is the power analyzer. We are not going to use another one because we don't need it. So I'd like you to actually take measurement from the reading here, and as I told you, I'll explain everything in another video, what to do with those measurements. So let's see. So the thing is, so I'll let me explain the circuit again. So this is the power supply. It is coming to the power analyzer's input, and the output will go to the primary side. Because this is an open circuit test, in one occasion there will be 2 cases. In one occasion we're gonna supply the primary side, and the secondary side will be open, and we'll do the same for the secondary side. So the secondary side will be powered by this power supply, and the primary side will open, and we'll actually measure everything, we'll calculate, we'll compare the results. So let's start doing it. So let's turn this on. So this is on. So let's turn the power analyzer on also. So this is also on. Let's switch it on here, the bottom section. Okay, that's tight. Okay, let me. So that is also on. I don't know why it was stuck. If we look at the voltage reading, there are some leakages, 0.001, so we can ignore that. So let's turn on, and like
let's increase the voltage. So as you can see, the voltage is increasing. Will actually supply the maximum amount of voltage on the primary side, so which is 145. So that's the supply voltage to the primary side, and the secondary side is open. Let's see, the power is 1 watt for this one, and power factor is 0.531. Supplied voltage is 144.6, and the current value is 0.013. Now with that, we are done with the first case. Now we are gonna reduce the voltage and make it 0, and turn this off, turn that one as well off. Now we'll switch, open this connection and connect it to the secondary side. Now we'll do the same. Let's turn this on, the main switch, and let's turn the power analyzer. Let's turn this on, dial it up, the voltage I'm talking about. So let's see, this is 10 volts. For the secondary side, I'm not gonna go beyond 100 volts. It is because we know the secondary side, this is a step down transformer, right? So this is a step down transformer. So the secondary side, if I supply 100 volts, say for example, the primary side will have double the amount, so it'll have 200. So I don't want it to be more than that, so that's 100 volts. Let's see. That's about it. So that's 100 volts to the secondary side. So what's the power here? 2 watt. What's the power factor? 0.582. Supply voltage to the secondary, having primary open, is 100.9, and the current is 0.034. That's it for today. So like do
Yes. So let's just give me one moment. Yeah. So we have we measured everything, I guess. Now I'd like you to actually take a note and make a table and put all the values and calculate each of these items. And then all you have to do is make sure in the report you put all the calculations thoroughly, just like this figure, way 1 for case 1, way 2 for case 1, and for case 2, way 1 and way 2. So I want you to actually put everything in the report, and the report structure I will give you in a second. Just a second. Okay. So in your report, all you have to do is you don't have to write the discussion or theoretical part. I don't want you to actually waste your time on this. You can read it out definitely, but it's not important for the report. So you need to write the purpose, report number, which will be experiment number 2, not 3, by the way. So the experiment name. Then I don't want you to write this one. I want you to write the procedure. So you'll need to write this procedure, but make sure that you change the value. So we didn't supply 240 volts, we supplied 140 volts. So you need to actually say that, write that. And also here we supplied 100 volts, not 120. So you need to actually make sure to correct it accordingly. And you need to write uh, like calculations. You need to put calculations in your report, and also you need to discuss the valid values that you obtain, um, and there will be some similarities, there will be some dissimilarities, mostly similar, but you need to actually identify that the errors. Like for instance, R1, if we calculate, okay, let's go back. So if, let me see whether I can put them side by side or not. Oh, I can't. Anyway, so whatever the values, like for instance, with the help of way1 equation, we will get RC1 and RC2. So the value will be pretty similar, like there will be a very minimum error. So you need to actually identify that, and you need to say why is that, because in some cases you used the measured sine wave, cos theta sine theta value, but in uh, in way one you actually used all the values you have calculated by your hand, right? So so there will be some deviation, but not that much. So same goes for xm and am2, but you will see a significant amount of change in with respect to like when we supply to the primary side and when we supply to the secondary side. So for instance, RC1 and RC1 of case 1 and case 2 will be totally different. You need to identify why is that. So you need to write in your report why there are some um, different values. So why those are different. So you need to uh, write an error analysis, and you need to draw a vector diagram. So let me give you an example of that vector diagram so that it will be easier for you to actually grasp the idea. So let okay. So let's use this space. Like for instance, if this is the circuit that we are looking for, this one is the circuit. So a vector diagram will look like something like this. I'm not gonna uh, like 100%, I will not draw it like entirely, but you will get some idea. So there is a current circulating here, and there is a current through this resistance and this inductance, right? So the name of this current is IR, say for example. It's very difficult to draw like this, and this is IX. So let's assume, since this is x-axis, it's easier to actually put E in a vector diagram uh, just along the x-axis. So we'll name it E. Again, it is very difficult to draw. So this is E. If this is E, the current along the resistive component will go on the same axis. So, and what about this one? It will be perpendicular to the IR. So it will be on this section. So I'm not gonna tell you how to draw the rest of it. So you need to actually identify the resultant current, which is IR plus IX. So you need to draw it by yourself, and you need to draw it with uh, the knowledge of scaling. So because the amount of EC or VOC is much larger than, say, for example, the current that is passing through this resistor. So you need to be careful about the scaling. So that's about it. You need to actually draw a vector diagram, and for both the cases, for case 1 and case 2, you need to draw two separate vector diagrams, and you need to analyze the errors while actually comparing the data. So that's about it. That's all for this open circuit test, but I'd like to show some other thing that I am actually preparing for you guys. So this is a single phase transformer lab. What you can do is you can actually experiment it in your home using MATLAB Simulink. So I will be providing you this one so you can do all sorts of experiments. So why I didn't actually give you this yet, because let's go back to the syllabus. So I want you to give this one after I'm done with this one, the efficiency part, because I want you to actually have the knowledge of experimental one, like for instance, calculating transformation ratio, open circuit test, short circuit test, and efficiency for different cases. So I want you to cover them all. Then we'll actually talk about this one. I will provide you that one. So with this setup, uh, you can actually experiment using only resistive load, only having inductive load on the secondary side, or capacitive load. You can switch everything. Like you can uh, you can make a combination of load, like for instance, RL load or uh, LC load or RC load or RLC load. And you can also perform open circuit test here and short circuit test here. And if you double click on any of the component, you will see the inside of this that source block, how many components you have. So you have an AC source, there are some function block here, and if you look at the sensors, so there are ammeters and voltmeters. So you can also do that. And this is the transformer block. So you have a transformer, non-linear, which is a practical transformer. So for open circuit test, you will have this, this will be closed. For short circuit test, this will be closed. So there are so many. So load side sensor, this is the load side sensors, and this is the load. So in some cases you will have R load, in some cases you will have capacitive load, some cases you will have inductive load. And you can definitely change the value of resistor by double clicking it, and you can change the value. But I not recommend you to do it. But you can do it definitely. And you can definitely see. Okay, it's not okay. So you can see the waveform. It's like an oscilloscope for MATLAB. So you can see the waveform of voltage and current. So the green one or yellow one is the source voltage, and this is the load voltage. So you can see everything. And there are some meters. So if you want to change the value amount of resistance, you can do it by uh, like if, like changing the dial. And these are all the values. Like say for example, I want to have a load which is RL, so I will switch them on, and all I have to do is run it. So after some time you will see that I will get some results. So these are the results. So it will, on the source side, which is primary side of the, I can see the measurement, voltage, RMS measurement, real power, power factor, current, RMS, uh, reactive power, power factor, angle, and apparent power. Same for the load side. So I'm gonna give you after we are done with the experiments. So that you can have your own, what is it called? You can actually tweak, and you can actually do it by yourself. So yeah. So that's about it. So if you again, if you have any question, you can definitely ask me anytime. And there are some people, students who are actually reaching out to me about some difficulties. So whenever they face any problem, they reach out to me. I'd like you all to actually reach out to me. Even if you don't have any problem, you can ask other questions, like for instance, related to this subject. So thank you so much for your attention. Have a nice weekend. Bye.